Swayam Prabha. Digital India. Educated India.
I think this most of you are able to get it correctly. There will be n minus 1 branches. Okay. Because if you have n nodes, that is n0, n1 up to n minus 1. Okay. So you will have one branch from n0 to n1 and another from n1 to n2 and so on. Okay. And you need n minus 1 branches to form a tree. Okay, I think all of you, most of you have got this correctly. Right? Now, once you have a tree, okay, it's very clear that if you add any more branches, if you add one branch, so you have a tree already. So let me redo this by numbering the branches. Let me redraw the circuit. I will label the nodes n0, n1, n2, n3, and I will call the branches A, B, C, D, E. Okay, there are 5 branches in this circuit. Okay, now I will identify a tree. This is my tree. Okay, n0, n1, n2, n3. And this particular tree I have chosen has these branches A, B and D. Okay. Now what I will do is, so as I said, first of all, if you have a circuit with n nodes and B branches, any tree you choose will have n minus 1 branches. Okay. So clearly the remaining branches will not be in the tree, that is B minus n minus 1 branches, not in the tree. Okay. We have a total of B branches and the tree has n minus 1 branches. So the remaining B minus n minus 1 branches or B minus n plus 1 branches will not be in the tree. Now what I will do is I will take my tree, which is shown here, and I will add one of the branches that is not in the tree. Okay, so in this case I have added branch C, and then I will add another branch which is not in the tree. Okay, so for this specific circuit, by the way, the number of nodes is 4 and the number of branches is 5. So n minus 1 is 3. We have 3 branches in the tree here, and B minus n plus 1 equals 2. Okay. So I have a possibility here and I have another possibility there. Okay. Now clearly, if I add a branch that is not in the tree to the tree, I will form a loop. Okay, that's very clear because I have gone through all the nodes without forming a loop. Now if I add any extra branch, it has to be between the same nodes. I have already covered all the nodes, so it has to form a loop. Okay, so this forms one loop and this forms another loop. Okay, so that means that the number of independent loops is B minus n plus 1. Actually, a couple of you had already got the answer, Aarti and so on. So we have B minus n plus 1 independent loops. Now I will just go through the argument once more for clarity. In a circuit with n nodes and B branches, we will have n minus 1 branches in a tree, b minus n plus 1 branches not in the tree. Okay. So now adding a branch to a tree forms a loop. Okay. And how many such possibilities are there? We have b minus n plus 1 branches which are not in the tree. So we go and add them on one by one to form each loop. So that means that we will have, from these two you can infer that there will be b minus n plus 1 independent loops. Okay. So this is some involved argument. So if you have any questions or any doubts, if something is not clear, please ask now. Now somebody asked what are branches? Any element is a branch, something that is connected between two nodes. Okay. Now we are discussing circuit at a more abstract level. Later we will go back to the specific circuit and put a resistor or a current source or a voltage source and discuss that. But right now any of those things can be a branch. Okay. Any questions? Okay, it appears that there are no questions on what we discussed this far. So now let's go on. Some of the other things will become clear as we move along. So far we have n minus 1 independent KCL equations and power adapter. We have b minus n plus 1 independent KVL equations. Okay, that is b minus n plus 1 independent loops. Okay, so we have a total of b equations. Okay, but we had two b variables, right? B branch voltages and b branch currents. So we need b more equations. Where will they come from? The question is between the KCL equations and KVL equations, together we have b equations. So where will the remaining b equations come from? We have two b variables, right? If we have b branches, we have b branch voltages and b branch currents. Where do you think the rest of the b equations come from? Because to solve for two b variables, finally we need to have two b equations. One of you said it comes from the VI relationship of each element, and that's correct. Some of you said Ohm's law, but Ohm's law is very specific to a resistor. So we have B elements or B branches. And each element will have its own VI relationship. So we have B, VI relationships. Okay, and together we have 2B equations. Okay. So with this we can solve for the 2B variables, which are B branch voltages and B branch currents. Okay. So I hope this part is clear. Right now we have discussed this analysis only at a high level, that is we didn't go and analyze any specific circuit, but we only discussed how to set up the equations, right? Now there are many ways of going about this. First we can look at some simple circuits, see how to analyze them. Now I have chosen to go in the other direction. I will first show you how to analyze any circuit. This is applicable to circuits of any complexity. Okay. Now of course you will not, if you have 100 nodes and so many branches, you will not analyze them by hand. You will not be doing hand calculations. You will set up the equations on a computer and solve it. But this method will be applicable to those things as well. Okay. So given this, now we can go and start with specific methods of circuit analysis. Okay. Is this clear? Any questions? Okay. Now there are two methods of circuit analysis. First is called nodal analysis. In this, what you do is you start with KCL equations at the nodes. Okay. And once you put down the KCL equations, you will solve for a number of things, and then you solve the complete circuit. So the first thing you do is to write down the KCL equations, and if you do that, you are basically doing nodal analysis. The second method is loop analysis, where you start with KVL equations at around the loops. Okay. And if you do this, you are doing loop analysis. We will discuss this later, and a subclass of this is known as mesh analysis. Okay. So we will first start with nodal analysis and see what it's all about. Okay. So let me write down the original circuit I had. I had this circuit, and okay, let me call this I1 and I3. I'll call this R11, R12, R13, sorry, R23, R22, R33, R13. The reason for this naming will become very clear. And let me call this node N0. This is N1, N2, N3. Okay. Now I said that we'll start with KCL equations at the nodes. Okay. Now if we have n nodes, it means that we have n minus 1 independent KCL equations. That is, if you have n nodes, you will write this KCL at n minus 1 nodes, and at one of the nodes you will not be writing the equation. Okay. In this particular case, we have 4 nodes and we will not be writing the equation at one of the nodes. Okay. Alright, let me choose that to be this bottom node n0. Okay. Now, such a node, the node where you are not writing the KCL equation, is called the reference node. And again, the reason for this terminology will become clear. Okay. So, what I am going to do is to write KCL equations at n1, n2 and n3. In this case. Now, I just arbitrarily chose not to write it at n0. You could have chosen not to write it n1 and write it at n0, n2, n3, or you can basically, out of the n nodes, you can choose any one node and then say that you are not going to write the equation at that node. Okay. So, in my case, I will write KCL at n1, 2 and 3. Okay. Now, let me write the KCL at node n1. Obviously, the current in this branch plus the current in that branch plus the current in that branch plus the current in that branch equal 0. Okay. Now, I will also, because we are trying to do this systematically for very large circuits, I will use certain conventions in writing these equations. Okay. That is, what I will do is, I will have all the unknowns on the left hand side and all the knowns on the right hand side. Okay. And what are the knowns? What I mean by that is, are the independent sources. Okay. Independent sources in the circuit. That is, so for instance, if I write the KCL at this node, the current through R13 is unknown, current through R12 is unknown, R11 is unknown. All those things I will group on the left hand side, and this current flowing out is due to a current source, independent current source. So that's a known quantity, and I will push it to the right hand side. So the way I will write these equations will be summation of currents leaving the node equals any independent current into the node. Okay. So that's how I will write the equations. And finally, here I have taken a circuit with resistors and current sources. Later we will also add voltage sources and analyze them. Now I have to write the current in each of these resistors. Okay. And the resistor has a certain VI relationship. Now while writing the KCL equations, I will use that current voltage relationship for the currents through the resistors. Okay. So for instance, what is the current through this resistance R12? It will be the voltage across the resistor divided by the resistance value. Okay. So let me label that. For instance, let me call this current through R12 as I12. Okay. In this direction, going from left to right. Now we know that I12 will be equal to V12 divided by R12. Okay. the current through this resistor equals the voltage across the resistor divided by the resistance value. Also, what I will do is, I don't want to keep on writing this thing in the denominator. So instead of this, I will use the conductance form of Ohm's law, which says that it is V12 times G12. Okay, so when I write this, it is implicit that G12 is 1 by R12. Okay, that is the conductance of this resistance, this resistor. So I12 is the conductance G12 times the voltage V12. I will write it in this form because the equations will look neater. That's all. It's not nothing fundamental about that. Okay. And finally, what is this V12? It's the voltage between voltage across the resistor, or voltage at node 1 minus the voltage at node 2. Okay. So I have to use these voltages. So what I will do is, I will use the voltages at N1, 2 and 3. Now again, while choosing voltages, there are many ways of doing it. I could choose the voltage across R12 as the variable, across R23 as the variable, and so on. Now, to be systematic and to have a clean structure to the equations, what I will do is, I will not use those things, but I will use the voltage between N1 and N0, between N2 and N0, between N3 and N0. Okay. Now the definition of N0 is very clear. That is the node at which I am not writing KCL. Okay. All other node voltages I express as the voltage between that node and the reference node. That is between each node and the node where I am not writing KCL. Okay. So that I will say voltages at node N1, 2 and 3 with respect to the node N0. I will call these voltages V1, V2 and V3. Okay. So now it's very common to say something like the voltage at node N1 is V1. What is meant is that the voltage between N1 and the reference node is V1. Similarly, when you say the voltage at node N2 is V2, it is with respect to reference node. Never forget that a voltage is always measured between 2 points, 2 nodes. Okay. So again, between N3 and N0, it is V3. So I will say this is V3 and V2 and V1. Okay. So that's about the conventions. So what it just to summarize, in this method, which is called nodal analysis, I will start with KCL equations at n-1 nodes. I will choose some node and call that the reference node. I will not write KCL there. I will write KCL at the remaining nodes. And what is KCL? It is the sum of currents flowing out of the node equal to 0. The way I will write it down is the sum of currents, basically unknown currents going out of the node, equals the sum of independent source currents that are coming into the node. So if you have a current source connected to that node, I will push it to the right hand side. Okay. Now this is a very common thing to do. You have variables on the left hand side and independent things on the right hand side, and you solve for the variable. This becomes very clear as we go along. And finally, the currents in resistors, I will write them in terms of voltages across the resistors times the conductance. Okay, current in each resistive branch equals the voltage across that branch times the conductance. Now I have to write the voltages. Again, I will choose the variables in a systematic way. I will choose the voltage at each node with respect to the reference node as the voltage variables. Okay. If you have any questions about these definitions, please ask questions now so that we can go ahead with the circuit analysis in a smooth way. Any questions about any part of what I said so far? Now there is one question basically asking, instead of current sources, if we have voltage sources, what do we do? Right now let's not take that case. I'll first do it with current sources and resistors, and later we'll consider the case of independent voltage sources. Okay. So looks like things are clear so far. So now let me go ahead and write the equations in the manner I described. Now the KCL at node N1 will be the sum of these currents, current through R11, current through R12, current through R13, the sum of those equal the current flowing into this node, which is I1. Okay. So first of all, the current through this R11 is V1 divided by R11, or V1 times G11. Okay. And the current through this R12 is the voltage across it, which is V1 minus V2. Okay. We are always taking the current flowing away. So you take the voltage at this node V1 minus the voltage at the wherever the resistor is connected, that is V2, plus V1 minus V2 times G12, plus here we have V1 minus V3 as the voltage across R13. Okay. Now the voltage across R13 is V1 minus V3, and the conductance of that is G13. If I was taking the currents going away from this node, I would say minus I1, right? Because I1 is flowing in, that would be minus I1. But so let me first write it like this: minus I1 equal to 0. Like I said, all the independent sources I will push to the right hand side. If I have to push it to the right hand side, I have to look at the current flowing into the node. Okay. On the left hand side, I have all the currents flowing out of the node, and that has to be equal to the current flowing into the node. Okay. So as I said, I will put all the independent variables on the right hand side. Okay. Now at node N2, I will write it similarly. The current through R22 is V2 times G22. Okay, because the voltage across that is V2, voltage between this and the reference node. And the voltage across R12 is V2 minus V1. Okay. Now note that while writing the equation for node 1 for R12, I took the current from left to right. Now I will take it from right to left. Okay. That's because for every node I will write the equations in terms of currents flowing outwards. Okay. And the current flowing from right to left is V2 minus V1 times G12. Okay. I hope that is clear. And finally, if I take this R23, then the voltage across that is V23, because I want to take the current V2 minus V3 because I would like to find the current in that direction. So plus V2 minus V3 times G23 equals, that should be equal to all the independent current that is coming into this node, and I don't have any independent current source connected to this node, so this will be equal to 0. Okay. And finally at node N3, I have the current through R33, which is V3 times G33, plus the current through R23. Again, I will take it flowing away from node N3. Okay, that is, I will look at the current in this direction, and that would be V3 minus V2 times G23. Okay.